Hello, and welcome back to Complex Differential Geometry, where today we're continuing through Hodge theory on Kähler manifolds. Last time we left off, we had to break this lecture in two halves, and we just finished complex Hodge theorem. So today we're going to be continuing where we left off. I'm not going to do a recap today because it's pretty obvious where we were. We just finished complex Hodge theorem, so today, we're going to be talking about the Kähler identities, and we're going to see how Hodge theorem is affected by the Kähler identities and what the Hodge symmetries look like on Kähler manifolds. All right, so let's start. The Kähler identities. Again, we should center that title. Okay, so the Kähler identities are a set of three identities that hold on Kähler manifolds because of the properties of Kähler manifolds. The proof of the Kähler identities is beyond the scope of this lecture series, so we're just going to be stating them and looking at some of their consequences. So let me first state what the three Kähler identities are. So the first one is that we have the commutator of this operator L. Let me write that nicely. L is called the Lefschetz operator. We're going to look at what the Lefschetz operator does in a little bit and how it's defined, but for now, let me just write out the identities. The commutator of L with the adjoint Dolbeault operator is equal to minus I into the anti-holomorphic Dolbeault operator. So number two, we have L commutator with the other one, the conjugate or the anti-holomorphic adjoint Dolbeault operator. That one gives us plus I into the regular Dolbeault operator. And lastly, and this one, I think you can derive this from these other two, gives you the fact that the D Laplacian is equal to 2 times the Dolbeault Laplacian or the partial Laplacian, which is also equal to 2 times the partial bar Laplacian. So there's some algebra that you can use to get from here to these. Maybe it's a good exercise to try to see how you can do that. You'll need some of the properties on Kähler manifolds in order to show this. And so the big question now is, what are the Lefschetz operators? So the Lefschetz operators. The spelling is a little difficult. So Lefschetz operator. This is an operator that one can have on, I'm assuming on a Hermitian manifold. We'll see why in a second. The Lefschetz operator L is an operator that's defined on any L is defined for any Hermitian manifold M, J, H, right? So that's a Hermitian manifold. And now the definition of L is that L is a map that takes us from omega PQ on M to omega P plus 1 Q plus 1 on M. So it raises the degree by 2 in a very specific way, where it increases the holomorphic grade by 1 and it increases the anti-holomorphic grade by 1. So what does this mean? Well, the specific way in which the Lefschetz operator increases the degree by 2 is that it will take, let's say alpha is a K-form, then it will take alpha and it will wedge it on the left by omega, the fundamental form. Now we're concerned with Kähler manifold, so this fundamental form will also then be the Kähler form. So the Lefschetz operator is a contraction of the form with the Kähler form from the left. And so that's the Lefschetz operator. And we also define lambda, which is, this is called, same idea, Hermitian manifold, right? So this is called the adjoint Lefschetz operator. In fact, lambda is equal to L dagger. And it's defined so that it's equal to Hodge star inverse L Hodge star, which causes it to act in the following way. If we take the Hodge inner product of L applied on alpha with beta, then we get the same thing as if we took the inner product of alpha with lambda applied on beta. So that's the definition. I didn't write its signature, so its signature looks like this: omega PQ of M and it takes us to an omega p minus 1 q minus 1 on M. So that's the adjoint Lifshitz operator. We already know that the Hodge inner product of the two is preserved, where if L is acting on alpha, then lambda is going to be acting on beta. But as is indicated here, we get a p minus 1 q minus 1 form, which is 2 degrees lower than the original form. So we get a form that represents what would happen if we took the form and reversed the direction of wedging with the fundamental form or the Kähler form. So that's the way you would want to interpret that. So lambda acts in such a way that its inner product with alpha would give you the same thing as if you increased alpha by 2 degrees and wedged it with the omega fundamental form of the Hermitian manifold. So it's not exactly removing an omega, it's more like removing something that has the same effect as adding an omega on the other side. So that is what causes this peculiar definition of lambda, and it turns out to be, or is defined to be, the dagger of L, the adjoint of L. So that's why these two things are dual. One increases by 2 by wedging with omega, and the other one decreases the degree by 2 by undoing something that causes the Hodge inner product to be preserved. Why do I talk about this? We're going to get a little bit into the adjoint Lifshitz operator in a little bit, and something that is interesting about these two operators. But the other thing that immediately comes out of defining the adjoint Lifshitz operator is that the more common form of the Kähler identities is actually written in terms of the adjoint of the Lifshitz operator. So you'll usually see the Kähler identities written like this. It'll be written as a commutator between lambda and the Dolbeau operator, which will give us I times partial bar dagger, and lambda commutator with partial bar is going to be equal to minus I. Let me give you a plus here for symmetry. So, and here we have the adjoint Dolbeau operator. So this is an alternate form, or the more common form of the Kähler identities. The only reason why I gave these ones first is because they're defined in terms of the regular Lifshitz operators. And I just thought that it would be more satisfying that way, but they're usually written like this with the adjoints instead. So now that we have the Lifshitz operators defined, and especially the Kähler identities, we're now going to enhance the complex Hodge decomposition theorem with the Kähler identities to see how it simplifies on a Kähler manifold. Oh, oops. So probably undid that for a little bit. So let's go to the next page to start talking about the Hodge theorem. Hodge theorem, complex of course, Hodge theorem, Kähler enhanced. So how is it going to be Kähler enhanced? Well, we're going to be using the Kähler identities here. So the first thing we're going to do is we're going to use the fact that delta D is equal to 2 into delta partial bar. Because of this, what's going to happen is that delta partial bar respects the PQ grading of the forms that it's acting on, right? Because delta partial bar is a map between omega PQ and omega PQ, right? So it sends PQ forms to PQ forms. So if delta D now is equal to this, then it also must preserve PQ forms. But since delta D acts on K forms, that means that when we split the K forms, right? When we split omega K is equal to P plus Q equals K omega PQ, which we can do, right? A K form is a sum of a bunch of PQ forms. Then delta D will now enter into that sum. Like before we couldn't do this, but now what we can do is we can take this here, and if I move this over here, then this goes like this, and it will now be able to enter into here. P plus Q equals K delta D omega PQ. So if we have a form like that is a harmonic form, a D harmonic form eta, right? Then what we can say is that if we expand out the harmonic form, what we get is delta D sum over P plus Q equals K of eta pq, and now delta d commutes with this sum, and so what we get is sum over p plus q equals k delta d of eta pq equals 0. But that is termwise, right? That's for each pq grading. So that means that each eta pq is now also d-harmonic. Let me center that again. Lack of centering, a common issue in this lecture series. So what does this do for us now? What this does is that we had a Hodge decomposition in terms of the exterior derivative, or the d Laplacian, right? So that means that what we can say is we can start with omega k. I'm going to suppress the c and I'm going to suppress the m, because we're going to keep writing this over and over again. But these are the spaces. So what I'll write it once. So omega k m c, and I won't write it again in the next few lines. So this is equal to the harmonic forms. So this is just the Hodge decomposition. Hk of m plus d of omega k plus 1 c complex forms. Sorry, this should be k minus 1. This should be k minus 1 because d increases the grade, or the degree, and d dagger should be the one with the k plus 1. K plus 1, c, m. Right, so this is just regular Hodge decomposition. So what's going to happen because of this behavior over here is we're now going to get it so that this now splits, right, over the PQ boundaries. So then we get H, PQ, partial bar. You can do it with partial or you can do it with partial bar. We're going to be doing it with partial bar here. So plus, I'm going to split this D into two pieces. Partial plus partial bar. Remember, we can decompose it into two pieces. And we'll keep this like this for a moment. Plus partial bar dagger, or partial dagger plus partial bar dagger of omega k plus 1. Now, if we split the operators here into their own individual terms, then we can decompose these spaces further. So then we get p plus q equals k, harmonic pq forms with respect to partial bar, plus partial of omega p minus 1 q, plus partial bar of omega pq minus 1. That's how it splits, plus partial dagger of omega p plus 1 q, plus partial bar dagger of omega p q plus 1. That it splits into four pieces. Now the interesting thing about these four pieces is they're not all independent from each other. So if we use the Kähler identities in these forms, L partial dagger is equal to minus I partial bar, we're not going to prove this, but this implies an isomorphism between two of these spaces. I'm not going to draw these anymore. So this, you can just infer that this is going to have this inside. So this is isomorphic to partial bar of dot dot dot. And similarly, L of partial bar dagger is equal to plus I into partial, which implies that partial bar dagger dot 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 is isomorphic to partial. So because of these spaces are actually coincident. They're actually one on top of each other. So in this orthogonal decomposition, we don't need all of these spaces. The other two pairs are actually orthogonal to each other. So what this means is that partial should be orthogonal to partial dagger, and partial bar should be orthogonal to partial bar dagger. So the other two are fine in the orthogonal decomposition, but there's some redundancy. We can remove two of these spaces without affecting the overall decomposition. So on the Kähler manifold, we can write it in a much simpler form, where what we can do is we can write it as, can either write it as omega k is equal to the sum p plus q equals k of harmonic pq forms with respect to partial bar plus, yeah, let me put this bracket over there, plus partial of omega p minus 1 q plus partial bar, or partial dagger, sorry, of omega p plus 1 q, or you can write it as omega k equals plus p plus q equals k. Oh, I think this should actually be a partial. pq partial bar plus partial bar omega p q minus 1 plus partial bar dagger omega p q plus 1. These are the two independent ways of writing them. One of them comes from delta d is equal to 2 partial bar, and the other one comes from delta d is equal to 2 delta partial, right? And so these are the two independent Kähler enhanced, if I can spell enhanced correctly, enhanced Hodge decompositions. So that's it. So on a Kähler manifold, we get this really nice split of the forms that doesn't happen on any other manifold. On other manifolds, d-harmonic forms have nothing to do with pq harmonic forms. Even on other complex manifolds, they have nothing to do. They don't split cleanly along the pq lines. But on a Kähler manifold, because of the Kähler identities, they split along these lines nicely, and so the d-harmonic forms descend into the pq forms, and each of the pq forms are d-harmonic individually. So now that we have established this, what we want to do now is we want to talk about some of the consequences of complex Hodge theorem in the context of the Kähler identities and what that means for the symmetries in the Hodge numbers of Kähler manifolds. Okay, so consequences. We will look at the consequences of our actions. Consequences of Hodge decomposition on Kähler manifolds. Decomposition on Kähler manifolds. Right, so the first result that we're going to look at is called Hodge symmetry. Hodge symmetry. And this is going to be a symmetry in the Hodge numbers of a Kähler manifold. And in order to establish why this happens, let's first look at the conjugation behavior of the Dolbeault operators. So the first thing that we want to note is that the partial of alpha bar is equal to partial bar of alpha bar, and partial bar of alpha whole bar is equal to partial of alpha bar. We also have a similar set of identities for the dagger operators. So partial dagger bar, or partial dagger alpha whole bar, is equal to partial bar dagger of alpha, and partial bar dagger alpha whole bar is equal to partial dagger of alpha. Okay, so because of these, what we're going to try to do is we're going to try to relate the Hodge number of a PQ form, alpha, let's say that's a PQ form, and we know that alpha bar is a QP form. So we're going to try to relate these two, and you can see how we might arrive at something like this. So we're going to have to be able to relate the Laplacians of alpha and alpha bar. So let's see how we can do that. So delta partial bar is equal to partial bar dagger plus partial bar dagger partial bar. And so we will need to show that these are both 0. So let's say that alpha is already partial bar harmonic. So if we assume that alpha is partial bar harmonic, then we get that partial bar of alpha is equal to 0. And that implies that partial bar alpha bar is equal to 0, which is the same as saying that partial of alpha bar is equal to 0. So what we did here is first we took the conjugate of the entire equation. 0 conjugate is obviously 0, and then we use the identity, this identity, in order to establish the second implication. So the second thing that we need to show is partial bar dagger. So let's say that partial bar dagger alpha is equal to 0, which implies that partial bar dagger, again, we're going to take the conjugate, is equal to 0, which implies that partial bar dagger bar alpha bar is equal to 0, which implies that partial dagger alpha bar is equal to 0. Which means alpha bar is partial harmonic. So if alpha is partial bar harmonic, then alpha is partial harmonic, which means that delta, or in other words, delta partial bar of alpha equals 0 implies that delta partial of alpha bar is equal to 0. But since these are actually equal to each other, that also implies that delta partial bar of alpha bar is also equal to 0 on a Kähler manifold because of the Kähler identities. So we find that the PQ harmonic forms and the QP harmonic forms are isomorphic to each other, the details of which would need to be worked out, but they're isomorphic to each other. You'd have to show the bijectivity of this map, but since we've established this alpha to alpha bar mapping, which I'm claiming is bijective, we therefore find that HPQ of M is isomorphic to HQP of M. Obviously on a complex manifold, that part's kind of implied, right? So the dimensions of these are the Hodge numbers, and so the dimensions of the Dolbeault cohomology classes are the Hodge numbers. So how do we relate these? So HPQ is equal to the dimension of the Dolbeault cohomology group HPQ partial bar of M. But because we know that there's a unique harmonic representative and therefore it's isomorphic, so we know that this is equal to the dimension of HPQ partial bar, which now we know is equal to the dimension of HQP partial bar, which is equal to the dimension of, unfolding it back up, HQP partial bar, which is equal to HQP, the Hodge number. So a lot of HPQs and HQPs in here. Hopefully the visuals helped in figuring out what I was talking about, but essentially the Hodge symmetry is this thing. It's the fact that the PQth Hodge number is equal to the QPth Hodge number. This is called the Hodge symmetry on Kähler manifolds. Right? So that's the first consequence of the Kähler identities and the Hodge decomposition. So now we're going to go on to the second one. So that's the first symmetry on, or consequence of the complex Hodge theorem on Kähler manifolds. Before we get to the second one, we're going to talk a little bit about the Hodge diamonds that are formed, these diagrams that are formed from the Hodge numbers, and how we can visualize these symmetries. All right, so Hodge diamonds. Hodge diamonds. I forget at this point if we had already talked about them in lecture 8 or not in the live session, but I moved Hodge diamonds up to lecture 12 now because this is where they become relevant. And so even if we did talk about them before, let's talk about them again. At this point, Hodge diamonds are pretty self-explanatory. Well, we have the dimension of the Dolbeault cohomology groups, HPQ, partial bar, and this is the Hodge number, HPQ, right? And so for, let's say we have an m-dimensional manifold, right? M-dimensional complex manifold, then in this situation, we will have a bunch of Hodge numbers. So basically they'll start from 800, every manifold will have this. Then you have H10, H01. Notice that I'm drawing them in this diamond shape. H11, H20, H02. Yeah, so let's just make it that big. So then this would be H21, this would be H12, and then this would be H22, right? So this is a Hodge diamond, and so this is a two-dimensional complex manifold, two-dimensional complex manifold, and it would get bigger as you add more dimensions. You could make this bigger and bigger, and I think you've seen the pattern, but in order to be explicit, and let's do this in pink. So in this direction, we increase the holomorphic grade or degree, and in this direction, we are increasing the anti-holomorphic degree. Anti-holomorphic degree. So this is a Hodge diamond, and it's a diagram that allows us to visualize the symmetries in the Hodge numbers of a complex manifold. So we previously computed the Dolbeault cohomology groups of two different complex manifolds, which were in fact compact Kähler manifolds. One of them was CP1, also known as the Riemann sphere. Remember, because of that extra point at infinity, it turns into a sphere. And the other one is T, or if you prefer TC, the complex torus. The complex torus is a one-dimensional complex manifold, since it's a two-dimensional real manifold. And so let's look at the Hodge diamonds for these. If you remember, 800 would be, so these are the dimensions of the Dolbeault cohomology groups, right? So this would be for CP1, this would be 1, 0, 0, 1, and for TC, this would be 1, 1, 1, 1. And so these are these four Hodge numbers. So one thing that you can see is we have that it's more apparent in CP1 that we have this symmetry. This is the Hodge symmetry or the conjugation symmetry, because this is H10 and this is H01, right? And we said that HPQ is equal to HQP. There's another symmetry, which is the symmetry from here to here, and that symmetry is called Serre duality. This is actually a result from sheaf cohomology that we didn't get the chance to look into, but let's just state the duality. This says that HPQ is equal to HM minus P, M minus Q. And this works on any compact complex manifold. Complex manifold. This is not specific to Kähler manifolds. So with the Serre duality, we have this. Maybe let's color code that. I'm gonna underline that in pink. So that's Serre duality right there. And this is Hodge symmetry. Now, when we're going to talk about Calabi-Yau manifolds, it's going to get even more symmetric than this, or there are going to be certain Hodge numbers that have to attain certain values on a Calabi-Yau manifold. So next lecture, we're going to look into that. But for now, this is the symmetry, right? This is a visual way to depict the Hodge symmetry on any complex manifold, but we can visualize the symmetries on the Kähler manifold, of course, through this diagram. Now, of course, the Hodge diamonds get much more complicated in higher dimensions. We are looking at two 1D complex manifolds, so we get pretty simple Hodge diamonds here, but obviously these get more elaborate and less trivial in the higher dimensional cases. So the next thing that we're going to talk about, so this is the second consequence, you could say. We just looked at a way to visualize the first consequence along with Serre duality. Now we're going to look at the second consequence, which is that the odd Betti numbers are even on Kähler manifolds. That's a little bit of a tongue twister, or hard to parse what that means. It'll become apparent in a second what we mean by odd Betti numbers or even, but this is the second thing. So where do Betti numbers come from? Betti numbers are actually related to the Hodge numbers on a Kähler manifold, and this has exactly to do with the fact that the D Laplacian and the Dolbeau Laplacians are equal to each other up to a scalar factor, and the fact that the D harmonic forms descend into PQ grading, that's what allows us a relationship between the Betti numbers and the Hodge numbers. That's what we're going to look into in this section. So the way this works is that, remember that we split up HKdR of M into set of P plus Q equals K, a sum, a direct sum of Dolbeau cohomology groups. Why did I write G? Partial bar M. Right? But that means that the dimensions of these has to line up too, which means the dimensions of HKdR, I'm going to suppress the M for a moment, is the sum. Well, now let's write the sum like this. P plus Q equals K, dimension of H, PQ, partial bar. So this is a Betti number, right? Because it's the dimension of Diram cohomology group, Betti number. And this is a Hodge number because it's the dimension of a Dolbeau cohomology group. But this is only true on a Kähler manifold, right? So this result is still specifically Kähler. So we call that BK is equal to the sum of P plus Q equals K, H, PQ. So this is true for Kähler manifolds. So you could even think of that as a sub-result. But this means that what we can do is, if we say, let's think of B2K minus 1. This is what I mean by odd Betti number. This is an odd number, right? If K is an integer, then 2K minus 1 is an odd number. This will give us the sum of P plus Q is equal to 2K minus 1, HPQ. So then that's equal to, if we rewrite that, that's equal to HPQ plus HQP of, if we rewrite it, we have to avoid double counting. So we're doubling them up. We're pairing the, let's say, H12 and H21. So in order to avoid the double counting, we have to say that P is less than Q, and both of these are up to 2M. And because of Hodge symmetry, we can rewrite this. Let me rewrite it here as HPQ, but then we get an extra 2. So we get this is equal to 2 into sum over P plus Q equals 2K minus 1. P is less than Q, 2M, HPQ. So whatever this is, it has to be an integer, right? Because all of the Hodge numbers are integers. So no matter what Hodge number we add up, their sum has to be an integer. But if it's 2 times an integer, well, that's an even number. This is an even number, right? So that means that B2K minus 1, an odd Betti number, is even. I hope that makes sense. That's what we mean when we say that odd Betti numbers are even on Kähler manifolds, because this is only true on Kähler manifolds. So that is the second consequence of the Kähler identity. So the next thing that we're going to talk about is the partial bar lemma. Remember the last time in lecture 11 we said we invoked this lemma, but we said that we're going to need the Kähler identities in order to prove it. And we're not really going to prove it. We're going to just give like an overall justification of the partial bar lemma. The full proof is very long and requires some understanding of Green's functions. So we're just going to give you an idea of why this is true. And yeah, but we do want to show how the Kähler identity is linked to the partial bar lemma, and why, for that reason, because the Kähler identities are only on the Kähler manifolds, therefore the partial bar lemma holds for Kähler manifolds. Okay, so let's get right into it. Partial bar lemma is the idea that on a Kähler manifold, let's say that alpha is a PQ form on a Kähler manifold, if it is partial closed and partial bar closed, partial bar closed, and also D exact, then there exists beta, a p minus 1, q minus 1 type form, such that alpha is equal to I partial bar beta. And that's where the name partial bar lemma comes from. So we need to prove that this beta exists, and that's what we're going to do next. So let's get right into trying to, well, this is going to be a justification. Justification. So this is not going to be airtight. We're going to be skipping steps, but it will show you why this might be true. So first step is to note that, let's say that we have alpha. Let alpha be a differential K-form, right? And so the way we can rewrite alpha is that alpha has a harmonic part and a non-harmonic part. Now, we're going to use something called G, the Green's operator. Green's operator. You can think of this as a kind of sort of like an inverse to the exterior derivative, but with a catch. The catch is that the Green's operator will take the harmonic part to 0, right? And so the Green's operator is not a true inverse, it's something called a pseudo-inverse, because that part that it's going to take to 0 cannot be re-inverted back to its original place. We've lost some information. So this is a pseudo-inverse. So we're going to add the harmonic part of alpha, which we're going to be calling eta. So alpha is equal to eta plus delta d, the d Laplacian, into g, or after g. And let's write it like this then, right? After g of alpha, right? So this is the harmonic part, harmonic, and this is the non-harmonic part. So that's the first step, to decompose our K-form alpha into two parts, the harmonic and the non-harmonic part. And so number 2, since eta is D exact, we already stipulated that, but it's also D closed and D closed. Why is it D closed? Because delta D is equal to delta partial, right? And therefore, if it's partial closed, it has to be D closed. And so this means that eta must be equal to 0, which implies that alpha is equal to delta D G alpha. So there is no harmonic part. Only the non-harmonic part remains. Number 3, step number 3 involves expanding the D Laplacian. So alpha is equal to delta D G alpha, which is equal to 2 delta partial bar, right, there should be a 2 here. Let's say partial bar, 2 partial bar G alpha. Let's expand this out. 2 partial bar dagger plus partial bar of G alpha. Now here we're going to need to use some commutation relations. So number 4, commutation relations, partial bar of G of alpha, or if you prefer, partial bar after G of alpha, is equal to G after partial bar of alpha. So because this is true, this line here, we can rewrite it as 2 partial bar dagger of G alpha plus partial bar dagger G of partial bar alpha, right? And remember, alpha is partial bar closed, so this is 0. Specifically, what we're saying is that partial bar of alpha is equal to 0, right? So then that means that we have one thing left, which is that alpha is equal to 2 partial bar dagger G alpha. So now we're almost to the home stretch. Step 5 will be to use the Kähler identities to show that partial bar dagger of G alpha which is this part over here, is equal to minus I lambda. So now we're using the adjoints, partial G alpha, right? Because this was the, we're using the first Kähler identity, right? So that gave us the commutation relation. We're just substituting back in the commutation relation. We've taken the I to the other side. So if we do that, we get, now let's expand out the commutation relation, minus lambda partial G minus partial lambda G alpha. And now we use the fact that partial also commutes with G. And so we get that this is 0 because we get G partial alpha, and partial alpha is 0. So let me undo that to give myself some space. This minus sign will multiply with this minus sign, and we get overall I partial lambda G alpha. So if we substitute this back into alpha's expression, we get 2 partial bar, and then we get I partial lambda G alpha, which is equal to I into partial bar partial into 2 lambda G alpha. If you want to be, sorry, that should be a partial. Which, if you want to be petty, we can rewrite this as I partial bar minus 2 lambda G alpha. What I did there is I commuted the partial and the partial bar. The commutation adds an extra minus sign, and I moved that minus sign inside the bracket because we want to identify this as beta. And that completes the proof. We found what beta is supposed to be. It is equal to partial bar beta, where beta is equal to minus 2 lambda G alpha. There you go. So that completes the proof. That's how we proved that whenever you have an K-form alpha, this is a K-form, it's also a PQ form, right? So then this would be a P-1, Q-1 form, right? So there you go. So now, with partial bar lemmas linked to the Kähler identities established, I mean, we use the Kähler identities in order to prove this lemma, right? So, or justify this lemma. And so now with that established, we will now get on to our last consequence for the Kähler manifold, and that is called Lefschetz decomposition. And this is turns out to be one of my favorite topics, which is weight space decompositions. But unfortunately, since we are not familiar yet with representation theory, I'm going to keep the representation theory side minimal and just explain what the Lefschetz decomposition on Kähler manifolds is. I'll give a brief peek into how it's similar to the SL2 algebra, and I'll give you some resources on where to look for some more ideas about weight space decompositions, because I think that's very cool topic in mathematics, and that's where we get the ladder operators in quantum mechanics from, for example. So in order to define the Lefschetz decomposition, we're going to need to know a specific kind of cohomology class called a primitive cohomology class. So these are different from the Dolbeault cohomology classes. How do we define them? Well, first of all, let M, J, G, omega be a Kähler manifold, a Kähler M manifold, and such that for any k between 0 and 2m, we get this set, pk, this is the cohomology class. This is defined to be a cohomology class alpha, element of, so this is a de Rham cohomology class, such that lambda of alpha is equal to 0, or equivalently, L to the power m minus k plus 1. So the difference between m and k inclusive is 0. So you can think of the primitive cohomology classes as these kind of prime factors of each of the de Rham cohomology classes, and we'll see exactly how this works using the Lefschetz decomposition. So the Lefschetz decomposition says that hk of m is equal to a direct sum for every r greater than or equal to 0 of L to the power r. So this is the Lefschetz operator applied r times. So what we're saying here, as usual, is L times after L r times of p k minus 2r. So this is not a power. This is the superscript of the primitive cohomology class on M. We can also rewrite this if you want to expand out this sum, we can rewrite this as p to the k m, that's for r is equal to 0, plus, for let's say then r equals to 1, we get L of p k minus 2, r equals to 1, right? And then we get plus L square p to the k minus 4 m plus ... We get more and more of these, and eventually we can get an infinite number of these capped by the manifold dimensions. So this is the Lefschetz decomposition, this thing, or if you prefer this thing, this is the Lefschetz decomposition. And so these primitive cohomology classes, what they end up being is, if we look back at the condition here, they're kind of the cohomology classes. Why are they primitive? They're the primitive cohomology classes because if you use the lowering operator, remember we said that lambda is the lowering operator, it decreases the degree of the k form by 2, p minus 1, q minus 1, right? In such a way as to preserve the inner product, the Hodge inner product. And so this cohomology class is such a cohomology class that cannot be produced by the action of wedging omega, the Kähler form, any number of times from the lower cohomology classes. Any attempt to do that will result in 0. So in that sense, we have the pk of m is a primitive class. It is the purest form. Then we have plus the k minus 2 forms, right? The k minus 2 forms that can be upgraded using the the Lefschetz operator to turn into k forms. And then we have the k minus 4 forms that can be turned into k forms using 2 Lefschetz operators. So in some sense, the pk forms are the ones that you can't get by wedging with omega some number of times. So these are, in that sense, let's use a different color, primitive. And that kind of is why we have this idea of their kind of like the prime numbers of the cohomology group. So there is in fact a secret SL2C representation here, which is really interesting. So let me make that explicit. In order to find the SL2C representation, we need to define one more operator. That operator is H, and it will be our counting operator. So that takes omega pq forms, and it gives us omega pq forms. I'm suppressing the m here, so that H of alpha is equal to, by definition, the dimension of the manifold minus p plus q, or you can call that k if you'd like, of alpha. And it counts the difference. So this is the middle point of the manifold. You can say it's the complex dimension, or you can say it is the half of the real dimension. And what H counts, the factor it pulls out, is the difference between the middle dimension and the degree of the k form alpha, where we're saying that p plus q is equal to k. So this is the counting operator. Now, this forms a certain Lie algebra where we get HL, the Lie bracket of this will be equal to 2L, then we get that H with lambda, the adjoint Lefschetz operator, is equal to minus 2 lambda. And then with L and lambda, this is equal to H. Now, this is eerily similar and in fact isomorphic to the SL2C Lie algebra. So this is the same thing as H, E is equal to 2E, H, F is equal to minus 2F, and EF is equal to H. So here, E is called the raising operator, raising. It raises the weight by 2, and F is called the lowering operator. It lowers the weight by 2. We're going to get into what that means. And lastly, that H is considered the counting operator, and it counts the number of degrees that we move, right? So why do we call them raising lowering operators? Because they fulfill this neat relationship where they look like this. So let's say that we have the de Rham cohomology groups H0M, and then we have the next one over H2M. Remember, we're increasing and decreasing the degree by 2. H4M. In fact, let me skip that. Let me do a little dot, dot, dot. And then we'll have, at the very end, we'll have HK minus 2M, and then we'll have HKM. And so the sense in which these are raising and lowering operators is that I can go between these two using L. It increases my degree by 1. Each of these can go with L. And then if I use, let me make this smaller so that I can make this point. If I use L on, this is called the highest weight state, then we get 0. Similarly, if we can go down a level by using lambda. And this looks a lot like a ladder. And then we can go down here also with lambda, and this gives us 0 as well. This is called, in physics at least, this is called the SL2C ladder. And in math, this would be called a weight space decomposition. Weight space decomposition of this representation, of the L lambda H representation of SL2C. This SL2C is supposed to be this like fancy fractal font. I can't really write it that way, but you'll have to kind of imagine that it's this like very angular font, SL2C. So that's really interesting that we get a representation of SL2C. So let me give you a brief idea of what a representation is. A representation is a set of linear operators. So these are the linear operators. It's a set of linear operators on a vector space. Sometimes the vector space is also called the representation. The vector space in this case would be these de Rham cohomology groups. So it's a set of linear operators that act as the analogs with the same structure, analogs with the same structure as a group. In this case, the group is the Lie algebra of SL2C. So if we go back down, this is what we consider the structure. It's these three relations that kind of lock in the multiplication structure of these three elements. And of course, for our case, E is L, the raising operator, F is lambda, the lowering operator, and H, pretty self-explanatory, H is capital H, the counting operator. So that is the last of the consequences on Kähler manifolds of the Kähler identities. So we're home stretch. Well, we're done actually. So that's it for lecture 12. We have looked at the Hodge theorem, its consequences on Kähler manifolds, and now we are ready to look into Calabi-Yaus. So before we do that, before we close for today, let's do a bit of a recap of what we did in the last lecture. So number 1, we defined a bunch of operators. I'm going to be a little bit more summary here. Bunch of operators, first we defined the volume form, right? Vol G or Vol H. Let's focus on the complex part. So we defined that. That allowed us to define the complex Hodge star operator, which allowed us to define the complex Hodge inner product. And then from that, we defined at the adjoint operators partial dagger and partial bar dagger. And that allowed us to define delta partial and delta partial bar, the Laplacians, the Dolbeau Laplacian and the conjugate Dolbeau Laplacian, or the partial Laplacian and the partial bar Laplacian. And then we use that to define harmonic forms with the idea of harmonic forms in tow, partial bar alpha is equal to 0 or delta partial alpha is equal to 0. These are our two harmonic forms. This is partial bar harmonic, and this is partial harmonic. We then were able to state Hodge theorem. And without the Kähler identities, Hodge theorem has three main statements. It says that the Dolbeau cohomology group is isomorphic to the set of PQ harmonic forms, assuming you map over the multiplication from one to the other. And then number two, if you take the harmonic forms, they're finite dimensional. Sorry, these are not in the same order that we found them out. Finite dimensional. And number three, we found the Hodge decomposition. Hodge decomposition that omega k is equal to h k plus d of omega k minus 1 plus, I'm being very accursory here, just to get the point across. So this is our Hodge decomposition without Kähler manifolds. So once we had Kähler manifolds, we could impose, number 4, the Kähler identities. Kähler identities, this is the first thing that we did in this lecture. Identities, which were L and partial. Let me scroll back up to my notes to make sure I got them correct. Right, so L partial dagger is equal to minus I partial bar. L partial bar dagger is equal to plus I partial, just regular partial. And also you can rewrite these as delta D is equal to 2 delta partial is equal to 2 delta partial bar. These are the Kähler identities. These are independent, and this is kind of a result of these. So with these in tow, what we could derive is that the K forms, or that delta D commutes with a sum over P and Q, and it distributes over each PQ form. And so we got that omega K is equal to a sum over P plus Q equals K, H PQ partial plus partial of omega P minus 1 Q plus partial dagger of omega P plus 1 Q. And there was a similar one with partial bar. So this was the Kähler enhanced. This was Kähler enhanced. It's not actually called the Kähler enhanced Hodge decomposition. That's what I'm calling it. Hodge decomposition. And lastly, we looked at some consequences. What were the consequences we looked at? First, we looked at Hodge symmetry, and then we visualized that using Hodge diamonds. We looked at Hodge symmetry plus Serre duality, Hodge diamonds plus Serre duality. And then number 2, we looked at the odd Betti numbers. 3, we looked at justification for the partial bar lemma from the Kähler identities. My penmanship is going down the drain now that we're close to the end. And number 4, the last one that we did was Lefschetz decomposition. Lefschetz decomposition, and we looked at it being a representation of SL2C. I'm not going to try to mimic that font again. So, oh, right. I forgot last time to talk about a reference for weight space decompositions and such things. So if you want to look into representation theory and weight space decompositions, one book that I found, I'm not really good at finding books, to be honest, but if you have a better book suggestion, please leave it down below. But I found Fulton and Harris, Representation Theory, a first course. This seems to cover most of the material, although I couldn't really find one that really delved into weight spaces and root spaces and all that kind of stuff. But that's the interesting stuff. That's the part that people don't usually talk about, at least in a first course in group theory. So if you want, you could look up all that stuff, look up weight spaces, look up root spaces, and that's where all of this sort of mathematical treatment for what we call ladder operators comes from. Okay, so that's it for today. Next time, let me draw another line here. Next time, what are we going to do? We're going to finally talk about Calabi-Yau's. Next time, Calabi-Yau's. And a little bit of a spoiler, I found out that just like how with Kähler manifolds, we had 4 different definitions, with Calabi-Yau's, we're going to have about 4 or 5 definitions of how you can come to Calabi-Yau from a Kähler manifold. So it's going to be interesting. Hopefully, we can summarize it to the point where it doesn't need to be 2 different episodes, but we will see. At least there's only 1 episode left to go, and we're going to look into how the Calabi-Yau's even further restrict the Kähler conditions. So, see you next time on Calabi-Yau manifolds, which is going to be our last episode for the lecture series.